Hello, everyone. I'm Shaoyi Huang, and I'm a second-year PhD student in Computer Science and Engineering Department at University of Connecticut. Today, I will talk about our work on an automatic and efficient BERT pruning for edge AI systems. This work is done by Shaoyi Huang, Yueying Liang, Hongwu Peng, and Seven Ding from University of Connecticut, Ling Liu and Hongjia Li from Northeastern University, and Dongkuan Xu from the Pennsylvania State University, and Mimi Xie from University of Texas at San Antonio. Natural language processing is quite a hot topic recently. Language is a data format which is made up of sequences of words. It's closely related to people's daily life as well as related applications. When communicating with people from other countries speaking different native languages, machine translation apps help us understand each other. Chatbots are frequently used to answer questions. Siri responds to our questions in a timely manner. These are some applications of question answering. Sentiment applications like social media monitoring, customer support management, and analyze customer feedback help to determine the sentiment expressed, like positive, negative, or neutral. Thus, help companies to analyze user survey responses, online reviews. Information extraction helps extract and organize information from large unstructured text and save it to database. Here is a figure demonstrates the trend of the state-of-the-art NLP sizes with time. Number of parameters of SOTA model increases with the year. Although the model performance on different tasks is better, the huge number of parameters hinders its application on the device. The transformer architecture is quite popular in recent years since many state-of-the-art natural language models use it. This figure shows a typical transformer model, which consists of inputs embedding, output embedding, positional encoding, encoders, decoders, and the final linear layer and the softmax layer. The transformer model is famous for its multi-head attention, which runs through an attention mechanism a few times in parallel. For encoder, it's usually a stack of several number of identical layers. Each layer has two sublayers. For decoder, it also consists of several identical layers. Different from encoder, the decoder inserts a third sublayer. While for both encoder and decoder, they contain multi-head attention. Position was fully collected feed-forward network and residual connections. So we mentioned that the huge number of parameters hinders the deployment of model on devices. Recently, a lot of efforts are put into automatic weight pruning to identify the subnetworks for deep neural networks to achieve similarity as human experts. However, existing works are empirically constant for each time of some subnetworks. It takes several training epochs to recover the accuracy of the sampled subnetworks from estimating the performance of subnetworks roughly. The large amount of sampled subnetworks may take more than thousands of training or fine-tuning epochs during the sampling and the evaluation phase. What's more, we empirically find that there is a positive relation of the performance after fine-tuning and after pruning among different tasks on GNU benchmark. Here, these are two figures of RTE and MRPC. Each blue dot in all the figures represents a candidate, while the values on the x-axis and the y-axis stand for the accuracy or matrices values after pruning and the value after fine-tuning. The red line In each subplot is the auto-filling trending line. The positive slope of the trend line in figures indicate a linear mapping relation between the manner of pruning without fine-tuning and the manner of pruning with fine-tuning. So here is the AE-BERT workflow. In stage 1, we generate several pruning strategies, and each strategy will result in the same overall pruning ratio. We adopt the common pruning method, which eliminates the least absolute value of width, using the pruning strategies to the original dense model and produce some pruned candidates as pruning strategies. In stage 2, we evaluate the candidates on the training set, and the one with the highest subnet evaluation value will be the final best candidate after all the iterations. In the final stage, we fine-tune the best candidate from the former stage and obtain the final good subnetwork. Given the input and output as shown in the pseudocode, we first generate n candidates based on n pruning strategies, then we evaluate strategies and pick out the best candidates. Finally, we fine-tune the best candidates and get the final model. Here are our experimental setup. We used the Hugging Face Transformer toolkit to conduct our experiments. For BERTBASE, there are 12 encoders, and the hidden size is 768, and the number of heads is 12, and the total number of parameters is 110 million. We fine-tune the model on RTX 6000 GPU. We evaluate the interface time on Intel Gold 6244 CPU with CUDA 11.1 and the Intel i5 CPU and Xilinx U200 FPGA board. We implement a single encoder on the FPGA board. The experimental results on glue benchmark tasks are shown in Table 1. We can achieve the aimed prune ratio with limited accuracy loss by applying the proposed AE-BERT framework. To be more specific, for the paraphrase similarity matching task on MRPC, both the top 1 and the top 10 F1 score of the sparse model at a pruning ratio of 0.5 even exceed our own fine-tuned baseline. Furthermore, for STS-B, the Spearman correlation loss for the top 1 result is 3.0, while the top 10 is 2.4 at a pruning ratio of 0.7. On the natural language inference tasks, say QNLI and RTE, our proposed framework can limit the accuracy loss up to 1.7 for the top 10 results. A comparison of AE-BERT and a sparse BERT-BASE at higher sparsity, for example, 0.9 is shown in Table 2. The difference between the two comparison methods is that the sparsity of different encoders of AE-BERT may be different from each other, while for sparse BERT-BASE is the same. The experimental results show that AE-BERT can find better subnets than irregular pruned BERT-BASE on QNLI, STS-B, MRPC, and RTE. We also investigate the effects of knowledge distillation, or KD, on the fine-tuning stage. While we use 4 BERT-BASE and the best candidates as teacher and student, respectively, we use the layer-wise distillation loss instead of hard knowledge loss to update with. The experimental results show that the KD could further improve the performance of the best candidates on QNLI, STS-B, MRPC. There are 3%, 5.8%, 1.9% performance gains using KD loss respectively. In our experiments, we observed that a single encoder occupies 2050 550.4K and 692.8K resources for DSP, FFT, and LUT respectively, as shown in Table 3. As for the total hardware resources utilizations, DSP, FF, and LUT require up to 6,840, 2,364.5K, and 1,882.2K, and percentage of the resource utilization on FPGA as 30.1%, 23.6%, and 36.8%. The latency of an encoder is reduced to 17.23 milliseconds after optimization. So it satisfies the real-time constraints and makes it possible for various NLP tasks while operating on resource-constrained devices. We compare the latency and throughput of a single encoder with batch size of 1 on Intel CPU and Xilinx FPGA board, respectively. The latency or throughput of the single encoder for the CPU and FPGA are listed in the table. As a result, 1.83 times inference speed up on a single encoder compared to CPU. In conclusion, the proposed pruning method can generate well-performed simulations and hardware design on FPGA, accelerates the inference time of BERTBASE. So as the conclusion, we propose the three-stage AE-BERT method to achieve automatic pruning on BERTBASE without experience of human experts. In stage 1, we sample the subnetworks according to the strategies generated on the pruning constraints. In stage 2, we evaluate the sample subnetworks and select candidates with the best performance on glue. Then we consider this subnetwork with the highest potential to achieve the highest performance. In addition, we achieve fine-tuning free in this stage. We fine-tune the winning candidates from the previous stage and obtain the final smart models in stage 3. Experiments on 4 glue benchmark tasks show that our proposed method outperforms the SOTA handcrafted pruning methods. Experiments on hardware platforms FPGA show that there is a 1.83 times inference time speed up of a single encoder on FPGA compared to CPU.